All right, guys. So you'll see on the names on these slides presented by Scott Atchley. I am clearly not Scott Atchley. He is much taller and better looking than I am. He is the lead for the QHPC systems project within the Quantum Science Center. And so, this 10 minutes is really about the architectures in which we're looking at deploying. And so this is a view from Oak Ridge National Lab. This is a view from the Quantum Science Center. And that we don't believe, and this is a view from the facility over there, that we don't necessarily believe that quantum replaces classical computing. We see these two technologies as complementary. Now, one thing we do know for sure is that a quantum computer will need some amount of tightly coupled classical computing. He has HPC here. I would argue classical computing to assist with things like syndrome decoding, error correction, pulse control as we move into a fault tolerance regime. However, what we don't know is what types of computing will end up within this area. There are opportunities within FPGAs, within GPUs, and other types of technologies. This is still a very active area of research. The predominant information that we're getting right now, and this is our view from a facility that runs a lot of scientific computing applications, is that this predominant focus is that the applications will be loosely coupled between classical and quantum computing. However, we don't know this for sure. This is a rapidly evolving area. So what we're doing is we are deploying an architectural model in which we have a large-scale HPC cluster for scientific computing like Frontier. Lux is being installed as we speak today. In 2028, we'll be putting down Discovery. And we believe that this will loosely couple over either ESNet or other connectivity mechanisms to a quantum facility. So what the architecture we're looking at is we want to put HPC technologies within that quantum facility, a smaller scale amount of HPC technologies. These might be to support that initial, quantum control, syndrome decoding, other activities. But what we don't know is what are the other opportunities within hybrid applications for running on that HPC system. There was a very good talk from HPE about a week ago, maybe 2 weeks ago, that was looking at opportunities for mid-circuit calculations and for some sort of iterative approaches to kind of course correcting quantum calculations, right? So we don't know what the scale of resources there will be necessary as algorithms evolve. And there's a lot of kind of discontinuity within the community about this. At SOS this year, I had to go behind Robin Clout Boom from Sandia, who argues that there's absolutely no necessity for connecting these architectures and that Perrier-Kitchens or interns is a fine connectivity mechanism for connection between classical and quantum. The algorithms are changing. Just this week, we had a lot of good conversations about new ways that people are looking at these applications. And so, our view is we'll put the technology down. We'll figure out what the application use cases are. As the application use cases evolve, we'll modify the system's architectures. As I mentioned, as probably been mentioned several times here, Oak Ridge National Lab and the Quantum Science Center has multiple quantum test beds on-prem already. We have our Quantum Brilliance and our IQM. Ideally, we'd like to pull in others. We're also pulling on deploying this quantum architecture model, this HPC classical and quantum architectural model with our facility, our smaller clusters, and our quantum computers. We believe this will give our staff and our collaborators opportunities to explore these workflows outside of the control issues and understand, outside of the control opportunities and understand from our inside application perspective, our scientific computing perspective, what makes sense for these interactions. And we believe this actually fits well into the IRI, American Science Cloud Genesis purview of connected facilities. Scott's thrust as it's developing better and better understanding of the application use cases from the HPC quantum perspective, we'll then utilize this to build system models, procurement advisory tools, in which we look at the way our leadership computing and quantum computing facilities are connected and what types of HPC resources we need to deploy at both places, but with predominant view on the scale and connectivity requirements of that small HPC or smaller HPC co-located with the quantum computer. So, as we mentioned, there may be multiple latency regimes, right? So we'll have frontier through ESNet, which we're talking tens to hundreds of milliseconds. We might have HPC co-located with quantum, not for quantum error correction, where we're looking at tens of microseconds. And we also might have HPC co-located with quantum, in which we are looking at sub-microsecond connectivity. These are all doable with network technologies, with high-speed I/O and FPGAs and other approaches. We just need to find what the use cases are and bring the technologies to bear that make sense for this fit, and tools that allow us to simulate and play with the tools and extrapolate allows us to have a leg up in what the design for these facilities should actually be. So the talks that, what we hope to get out of conversations like today is, kind of understanding from the application from you guys, what you're seeing as the estimations for resource requirements coming out of the applications today in the NISC era and tomorrow in the fault tolerant era, and somewhere in between, in which we might have NISC and fault tolerant coexisting, and understanding what those workflows and workloads look like. And so what we want to know is the logical qubits, the circuit depths, the shot counts, the logical encodings. Do we use one logical encoding or multiple logical encodings? The application flops and memory requirements, how much I need to run on Frontier, how much I need to run on our co-located cluster, and how much interaction is necessary between the quantum computer. And then, as I mentioned, the latency and bandwidth requirements at each of the stages. So right now, we don't have a good fit for what the hierarchies are. This is just one. This is just one view. It might require deeper hierarchies or shallow hierarchies. This is a rapidly evolving area. So Scott put in here a few workflow patterns that we've been looking at within this project. So there's the single shot open loop. Classical computer does some modeling and simulation, generates its need out of the quantum computer, does the compilation of the circuits, pushes them out to the quantum computer. NISC today waits, a few seconds or minutes, in turn brings the result back to the classical computer and then continues its processing. But there's other things that are going on. We've talked to some chemistry apps who are looking at multiple shots of different materials or different molecules that they want to send out to get basis states, where we are, interacting more between the quantum computer and this batched and pipeline approach. You see a lot of this today in NIST, this variational and iterative optimization loop. There are some questions whether that remains in the future as we move towards fault tolerance. I think there are some in the room that believe we will. I'm slowly becoming one of those, particularly with mid-circuit opportunities, right? So one of the things I don't think, Scott, that really pointed out within these workflows is we have classical computation, but we have remote classical computation, local classical computing, quantum computing. And I think one of the things we need to understand in these workflow patterns is what happens at each step of the way. All right, so our next three talks. What we're hoping to listen for, and what I'm hoping to get out of this, and maybe you guys as well, the applications and algorithms. We need to know what the problems are. We need to know who to be talking to from our leadership computing, the folks on our systems. What are the classical problems we're trying to solve, and how are they going to incorporate quantum? What do they think the resource requirements are? What level of fault tolerance do they need? How deep the circuits are? How are they planning on using the systems? Their preferred workflow and system architectures. Clearly, we always, as a facility, have taken some of this with a little bit of a grain of salt, because as a HPC computing facility, We are generally forced to go where the technology is going. We had a lot of scientific users who weren't enthusiastic about porting their x86 code to GPUs, but here we are now, and there's many hacker campers who now don't want to pivot from GPUs to other technologies as these things are approaching 8,000 watts. And then, some of the lessons learned that you guys have had over the last couple of years working within this, what worked, what didn't, and where you guys feel the integration bottlenecks are. This is very important to the QSC. This is very important to OR now as we develop what these system architectures look like for our next generation computers. That's all I have to, hopefully that was close to 10 minutes. Thank you.